The use of language models in robotics is a relatively unexplored but exciting new research direction, and it has a few key advantages. The first is that it should be able to respond to human-style commands automatically, so the type of order that we give a human to do this or do that can be given straight to a robot and be understood. Secondly, language models have a large amount of knowledge from the data they're trained on that they can call on to enrich a solution. Thirdly, they can adapt to unexpected inputs. Something unusual happens that the designers didn't plan for. Well, a language model can have a good crack at trying to resolve that and come up with some interesting ways to approach new problems. And finally, they are transparent and explainable. Everything in the control flow from the start to the finish is modeled as text, so humans can understand what's been done and can also go in and potentially insert their ideas in the form of text into that control flow on the fly. We're applying the language-based approach to a collective planning problem that runs across sort of four stages. So we're going to model our robots as little cleaning robots that are going to move around the environment and clean different rooms in a building. So the first step is that the human is going to input a task which is interpreted by the large language models. So it is going to be a brief description of I need you to go and clean these rooms and do this. It might be specific or quite general. And we also can give it an image which is processed directly by the model, which can be a map of any kind that models the room, typically something that's hand drawn. Next is the planning stage. So each robot we have has a large language model that allows it to become an entity in the chat environment. And so we literally put our robots into a chat room and have them talk to each other by sending messages one at a time to discuss the task that has to be done, to break it down into subproblems, and to decide and assign who does what. Now that the robots have come up with a plan, they can actually try it. This is deployed straight onto the robots, and they're going to move from room to room, trying to solve the task in the way that they themselves planned out, and maintaining communication as they do it. Finally, the robots can coordinate and can actually dynamically update and replan if anything goes wrong. So if a robot discovers that it can't get somewhere, or that it made a mistake, or even that the large language model hallucinates, which is always a possibility, they can initiate a replanning process with their neighbor and have another go adjusting the plan on the fly to achieve the task. We will be demonstrating this as follows. Firstly, a human can write out a task in natural language, and we can provide the agents with a map hand-drawn of the environment and mark it somehow on the floor if we wish. Secondly, the language models will then take this task as a plan, along with a bit of instruction on how to debate. You can see that it's there in the initial prompt section. And then Alice and Bob, our two robots, will discuss in this chat room how they're going to solve the task, and eventually produce a plan, which is a path of rooms. The supervisor, the human this is, can inspect the plan, and if they want, they can request changes, or they can accept it. This plan is then deployed straight onto our two real robots. These are called Alice and Bob, and they're both Turtlebot 3s with bins mounted on 3D printed mounts above their LiDAR. We take our environment representation and then create an Aruco marker which represents each room. This is how the robots find their way around the environment. The robots use the paths that they just decided. They rotate on the spot until they can find the room that they can see, because they don't have an actual accurate map. They only have the flowchart we showed them. They find the rooms and they move to them step by step. We also encourage participants to stand at the side and put rubbish into them when they come to their room. The robots will maintain conversation as they move from room to room, and that will be shown on some kind of screen that we have nearby, so that participants can see the robots moving and can actually understand what they're doing, which is that they're having a conversation, and if they want to, the human can even step in and get involved in that conversation at any time. This conversation also, of course, facilitates coordination of the agents. Consider our previous example, but this time when Alice reaches the kitchen, she sees the eating area and notices that it's actually already been mopped, the floor is wet, it doesn't need to be cleaned, and more importantly, she actually can't pass. When this happens, a message is inserted which explains what's happened, and the robots begin a new conversation, or rather continue the existing one, but this time directed once again at planning how to solve the problem. In some situations where the task is more complicated, it might require a longer conversation as it did before, but in this situation it's a nice and simple one, so Bob immediately solves the task on his own. We can see here that the route is revised to one where Alice will backtrack back to home, to the hallway, and then to the conference room because she can't pass through the eating area. This lets us further use our language approach as a continuous coordination model rather than simply one of planning at the beginning.